Here we are discussing that how many stages does floating point unit have and what is the purpose of each bypass in floating point unit. But before that, we will see what is the floating point unit. Like the 80486 processor, the Pentium contains on-chip floating point unit. Prior to the 80486, an external coprocessor was used to perform floating point operations for the 8086, 80286 and 80386. This 8087 coprocessor. The simple fact that these coprocessors were outside the CPU increased the time required to perform a floating point operation due to the synchronization issues. Moving the coprocessor onto the same chip as the processor like 80486 and the Pentium allows a faster communication and quicker execution. The FPU, that is floating point unit, achieves its quick speed through a pipeline containing 8 stages. The first 5 stages, that is PF, DI, D2, EX up to XI. The operation are the one of that make a U pipeline which processes integer instructions. The operations of the fifth stage is different however and fits the remaining 3 stages that complete the floating point pipeline. Recall that fifth stage of the U pipeline was write back. When configured for floating point operation, the fifth stage becomes as X1. This is what the write back stage which comes to the X1, the first floating point execution stage. Here the Pentium processor FPU has 8 pipeline stages like prefetch, instruction decode, address generation, EX, that is memory and the register read conversion of floating point data, then X1 like write back, floating point execute stage 1 conversion of external memory from to the internal, then floating point that data format and write operand to the FP register file bypass 1. Next one is X2, floating point execute stage 2, WF perform rounding and the write floating point result to the register file bypass 2, and last one is AR, error reporting update status 1. Now we will discuss each stages of the floating point unit pipeline one by one. First, in prefetch stage. What happen in prefetch stage? The instruction are prefetched from the on-chip instruction cache. In second, instruction decode, that is D1 stage, 2 parallel decoders attempt to decode and issue the next 2 sequential instruction. It decodes the sequential instruction to generate a control word. A single control word causes direct execution of an instruction. Complex instruction required microcoded control sequencing. Next is address generation, that is D2 phase. In address generation phase, it decodes the control word which is generated by the D1 phase and the address of the memory register operands are calculated. The next phase is memory and the register read, that is execution state, EX states. In EX stage, register read, memory or memory write perform as a required by the instruction to access an operand. In the next phase, that is X1 phase, which is also called as a write back phase. In that, what happen? Information from the register or memory is written to the FP register and data is converted to the floating point format before being loaded into the floating point unit. The next stage is X2 stage, which is floating point execution stage. What happen in that? Floating point operations performed within the floating point unit. Then WF, that is write FP result. Floating point result are rounded in this stage and the result is written to the target floating point register, that is in FP register, which is in previous stage. Next one is error reporting, that is one last stage of the floating point unit. What happen in that? If an error is detected, an error reporting stage is entered where the prior error is reported and FPU status word is updated. But there are some instruction issues for the floating point unit. So let's see one by one. In FP instruction, do not get paired with integer instruction. When a pair of FP instruction is issued issued to the FPU only the FXCH instructions can be second instruction of the pair. The first instruction of the pair must be one of the set F, where F equals to FLD, then FADD, FA sub. Likewise, all the instructions are executed like fmul, fdivision for division purpose, multiplication purpose, etc. instructions are executed. FA instructions other than FXCH and instruction belonging to the set F always get issued singly to the floating point unit. The next issue is floating point instruction other than the FXCH is not directly followed by an FXCH instruction are issued singly to the floating point unit. Then we will discuss the second point, that is what is the purpose of each bypass in floating point pipelining. What happens in floating point pipeline? There are two different bypass connection. Bypass 1 connect the output. Here the bypass 1 connect the output of X1 stage to the input of EX stage. This is done to allow the floating point register write operation in the X1 stage to the bypass to the floating point register file, and the set the result to the instruction performing a floating point register read in the EX stage. For example, consider these two instructions. First one is FLD ST, then fmul, that is for the multiplication in ST. What happened? Both use the ST register as a operand. The result produced by the FLD must be available for the fmul instruction can proceed. Using bypass 1, the data from FLD is made available as an input operand for the fmul before it is written into the floating point register file. This prevents the pipeline for the stalling while waiting for the register file to provide a copy of ST. Overall, we get a decreases in the number of clock cycles required to perform many different combination instructions. This technique is also called as forwarding. The second type of bypass is like that. What happened in that? The second type of bypass takes place between the WF and the EX stage, where the result of arithmetic instruction in stage WF is made available to the next instruction fetching operand in the EX stage. The floating point register file contains the 80 bit of floating point register ST0 through ST7. The read and write section are dual ported. To allow to read or to write to take place simultaneously, as indicated in this figure. The two read ports send the data into EX stage. The two write ports receive the data from X1 and WF stage of the pipeline. Both bypass are shown to illustrate that how results are fed back from X1 and WF stage to the EX stage. The Pentium is capable of executing two floating point unit instructions at the same time under the special circumstances. But to do the some first instruction of the pair must be one of the following, like that. First, FLD, it should be single or double. F sub, F add, F com. Likewise, which we are discussing in the rules of floating point unit. The second instruction must be FXCH, since the U pipeline makes up the first 5 stage of FU pipeline. The FXCH instruction execute in the V pipeline. Since both instructions execute in parallel, FXH instruction literally requires 0 clock cycle. Normally, FXH requires 1 clock cycle when issued by itself. Since many of the floating point instructions use the operand on the top of the floating point stack, there is a good possibility of the stall when 2 instructions require the top of the stack operand. Using FXCH as the second instruction of legal pair helps avoid this problem. If the second floating point instruction in a pair is not FXCH, both floating point instructions are executed one at a time. If the second instruction is not a floating point instructions, it cannot be paired with the first instruction because the floating point unit uses the both pipelines, that is U and V, when fetching a 64-bit operand from the memory. This is what all about the floating point unit pipeline and the bypass in floating point unit pipeline. Thank you.